4.2 is about area under the curve. And 4.3 is about the definition of interval. Or the definite interval. If you remember, we talked about the indefinite interval in 4.1. The indefinite integral was just this antiderivative idea. Okay, the indefinite integral means you take the antiderivative and add c. The definite integral means the same thing as area under the curve, it turns out. We kind of have to talk about how the two are related, how definite and indefinite intervals are related. And in order to do that, I have to go through this garbage. It's interesting, it's just tedious. So I'll start here. So we'll talk about that under the curve. We'll do our best. In order to really talk about area, I have to talk about something called sigma notation, which you may have seen before and you may not have. We're going to be adding up a lot of numbers, right? So this idea of area under a curve, if you remember from the very beginning of class, I talked about you can estimate the area under a curve by basically building a whole bunch of rectangles and finding their area. All right, so this would be one way to estimate the area under the curve. You build all these rectangles, and then you just find the area of each one and sum them up. That will give you an approximation for the area under the curve. So if we're going to be summing up a bunch of areas, we want to have a nice notation for our sums. That's what we have to go through. So this is kind of an idea here. Sort of a compact notation to sum up n numbers. So suppose I just want to sum up n random numbers that I pick. I can write this in what's called sigma notation. This is a capital sigma, Greek letter. It looks like this. I'm going to tell you what each one of these means. So this notation means exactly the same thing as adding up n numbers. These n numbers. And I'll give you an example very quickly. But just sort of notationally, what you call these things, this guy down here is called the index. And it's kind of like a dummy variable. The index is going to start from 1 and go all the way up to n. So this is telling you I is the index, and this is telling you where to start. N is telling you where to end. The AI's in here are the terms that you're actually summing up. So like when I is 1, that's talking about A1. When I is 2, that's referring to A2. The sum is on A2. This guy, this I mean, it can be replaced with anything. You can make this a K, a goat, whatever you want. Right? But these should always match here. Right, if I have I equaling 1 and I put A sub W, that means something different. If this index doesn't match this guy, then this is a constant. So, and then you can really pull it out. So it means something totally different. So you want usually this index to match this little subscript here. But let me do a concrete example so you see what we're talking about. So evaluate each sum. So the sum from I equals 1 to 5 of I. this is just to help you understand what we mean by the sigma notation. So what do you think this means? Start from 1 and start plugging it into this formula. This is basically your formula for each term of the sum. So if you start from 1 and you plug 1 in here, it's just 1. If you plug 2 in here, so then move on to 2. Move on to 3. Move on to 4. Move on to 5. Move on to 6. No, I should stop at 5. So this sum is trying to tell me to add up 1, 2, 3, 4, and 5, which is 10 and 15. So maybe that was too easy to any impact. Sum from 1 to 3, sum from 1 to 3 of I squared. What's this mean? Start from 1, square it. Move to 2, square it. Move to 3, square it. Right, so the big sigma tells you it's a sum, which means everything is being added. And then this formula tells you how to get each term. Right, this I squared means you're going to square 1, square 2, square 3. The sigma tells you the sum of add them all up. So then you actually do it, I guess. 1 plus 4 plus 9. Sum from 1 to 10 of cosine of I pi. So if you write out what this means, you plug in 1, cosine 1 pi, and then what do? Plus cos 2 pi, plug in 2, plus cos 3 pi, and you keep going. All the way until you get to 10 pi. Just continue on in this pattern. Stop at 10, start at 1. What's this equal?
0.
It's equal to 0. Right, every 2 terms cancel out. Cosine of 1 pi is negative 1. Cosine of 2 pi is back to 1. Cosine of 3 pi is negative 1. So cosine of 4 pi will be back to 1. So you keep getting a bunch of zeros. So this guy will be 1, but the guy behind it will be negative 1. Which is 0. And we'll make it a little more interesting. So sum from 1 to 4 of negative 1 to the, oh, not n. I. Negative 1 to the I over I. So this just means you start with 1 and plug it in. Negative 1 to the 1 over 1 is your first term. Plus negative 1 to the 2 over 2. Plus negative 1 to the 3 over 3, plus negative 1 to the 4 over 4. And then you stop. Because you reach your stopping condition. Right, so you just go through and plug your i's in wherever you see an I. Add it all up. This will be negative 1 plus 1/2 minus 1/3 plus 1/4. Which if you did want to add up, you can make them all denominator 12. So negative 12 over 12, 6 over 12, 4 over 12, 3 over 12. will be negative plus 6, so negative 6 minus 4, negative 10 plus 3, negative 7. Okay, cool. So this notation is okay? What if I wanted you to go backward? So I could say, write each sum using sigma notation. Which is what these do. And I'll give you something like 2 plus 4 plus 6 plus 8. Okay. So now I'm giving you this side, and I want you to come up with this side. Yeah, so you have sigma. You have 4 terms, 1, 2, 3, 4 different terms. So I would do I from 1 to 4. Yeah, but then you have to think about, how do you change a 1 into a 2? You multiply by 2. Right? How do you change it? Think about the I underneath. This will be I equal 1. This will be I equal 2. This will be I equal 3. So you have to extract the pattern. What are you doing each time you're multiplying by 2? So you put 2I. The I counts which term you're on. So you can always write your index underneath, starting from 1 and going up, and then try to find the pattern. So 1 plus 3 plus 5 plus 9 plus 11, if I want to write it with this notation, hardest part is drawing a fancy signal. How many terms do I have? 1, 2, 3, 4, 5. So I'll probably do I equals 1 to 5. And then let me try and wrap my head around this. This is I equals 1, I equals 2, 3, 4, so compare it to these, right? These were all 2 times I. These are all related, right? Because 1 is 1 less than 2, 3 is 1 less than 4, 5 is 1 less than 6, 9 is 1 less than 8. Oh wait, that's wrong. Oh, I skipped one. You can't do this. This has to be 7. I skipped another number. Yeah. Yeah. The other one you would need 2 sums for because the pattern breaks. You have 2 sums.
Thanks for the warning there.
Yeah. Yeah. Sorry, I meant to put a 7 there. Okay, so what is this then? I was wondering why you guys are so quiet.
2i minus 1.
So is it 2i minus 1 or 2i plus 1? It's got to be minus 1. Right? Usually, you might want to put these in parentheses to indicate that it's all inside of the sigma. But yeah, these are the odd numbers, so you just, 2i is an even number, then you subtract 1 to make it an odd. As long as I write the right pattern. By the way, what if I throw some minus signs in there?
Times negative 1.
Yeah, so look on this example here. See how we had a minus, then a plus, then a minus, then a plus? To get alternating signs like this, you need a -1 to a, well, you don't need, but the easiest way is to have -1 to a power. Because when the power is even, you'll have a plus sign, and when the power is odd, you'll have a minus sign.
So it's the last one times -1 to the I minus or plus 1.
Yeah, so the numbers are all the same, which means I'm going to have the same formula for the most part. But then I have to add a negative, or I have to multiply by a -1. And now you have to pick which power to put it to. If I put an I up here, does that work?
No. It has to be I minus 5 plus
-1 to the I is not going to work because when you plug in 1, this will be 1, but this will be -1. And if you write this out, the first term will be -1 to the 1, which will make this negative. So you either have to have I plus 1 or I minus 1. They'll both accomplish the same thing. -1 to the I plus 1 times 2I minus 1. Right, because then when you plug in I equals 1, you get -1 squared, which will keep this positive. When you plug in 2, you'll get -1 to the third. So when I equals 2, you're getting negative. When I equals 3, you'll get -1 to the fourth, which is positive. So it checks out. Maybe one more. Okay, let's do -1/2 plus 1/4 minus 1/8 plus 1/16. This is going to be I equals 1, I equals 2, I equals 3, I equals 4. So I'll have a sum from 1 to 4 definitely. Yeah, now what's the pattern here? Do you guys see the pattern? Yeah, these are powers, well, one way to say it is that these are powers of 1/2. Or another way to say it is that the denominators are all powers of 2. Right? This is 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. So the easiest way to write this would be -1/2 to the I. Does that check? When I is 1, you get -1/2. When I is 2, you get -1/2 squared, which is positive 1/4. When I is 3, you get -1/2 cubed, which will be -1/8. So it checks. An equivalent way to write this, you might think, which is fine. If you notice the pattern in the denominator is always 2 to the I. And then the negative you can put with the numerator. Right? The negative is just making the numerator either positive or negative. So you can do -1 to the I on top. That'll give you the same. This way's a little more compact, but this way's equivalent. Either way, you have to recognize the pattern. You have to recognize your powers of 2, powers of 1. So we won't, we'll be doing a little bit of this. Not too much. So here's what we actually need to be able to do area. algebra rules. So if you take the sum from 1 to n of two terms, two functions here, being added or subtracted, you can actually distribute out the sum. You should be used to seeing rules like this. So what I mean, for example, if I wanted to calculate the sum from I equals 1 to 3 of I plus I squared, I could break that into two separate sums. I could do the sum from 1 to 3 of I plus the sum from 1 to 3 of I squared. I know you don't think this is ever going to matter, but it makes life a little easier sometimes. So you can distribute the sum, basically. You can put it to each term. Do you remember what other rule we usually have with this? When you can distribute, like with derivatives, the same rule applies. With integrals, the same rule applies. There's another one that always goes with it. Constant multiple. If you have a constant multiple in front, you can pull it out. Like this. If you're doing the sum of k times ai from 1 to n, that k can be pulled out. K is a constant. So, what we're going to need when we actually start doing when we actually start doing Riemann sums, when we start doing the calculus portion, is what some of these common sums add to. So, for example, the first one, if I want to add up the number 1 for I going from 1 to n, what do you think this is going to be? You know what this means? Like if you were going to write this out, what would you write out? What happens when I equals 1? What does this equal? 1. What happens when I equals 2? What does this equal? Still 1. What happens when I equals 3? Still 1. When I equals 4? Still 1. How high do you go? Until you get to n times. So if you add up 1 n times, what did you get? If you add up 1 5 times, what do you get? 5. If you add up 1 10 times, what do you get? 10. If you add up 1 n times, what do you get? 10. This one's not. This one would be, you'd have to add up 1, 2, 3, 4, 5, 6, 7, all the way until you got to n. This one is not quite as easy. You don't have to memorize this. I'll always give you these if you need them. This one is n times n plus 1 times 2n plus 1 over 6. I don't know how to prove this. I have to look it up, but I don't remember. the two. This one maybe. These two, I don't know. Let me give you some examples. So we make sure you can use these formulas. All right, so if I wanted you to find the sum of the first, so find each sum. And I want the sum of the first 100 whole numbers. So this guy is saying, basically, add up 1, 2, 3, 4, 5, all the way until you get to 100. That's what this means. Thankfully, we don't have to do all this. We have a formula for it. This should be ends. Should be ends. I is an index. I change this all the time. Should be ends. So you can just plug it in with n equal to 100. You plug in n equals 100 to this formula here, you get 100 times 101 over 2. So this is more like what we're going to be seeing. Oh, that should be I. So summation I equals 1 to 1,000 of 1 plus I over 1,000 times 1 over 1,000. So kind of the game with these things is you don't want to add up 1,000 anything, right? It's going to take you forever. So instead, you want to use one of these formulas. But you have to kind of manipulate it first in order to make it look exactly like one of those. So for example, this 1 over 1,000 is a constant multiple. So it can come out front by my constant multiple. Does that make sense? It doesn't have an I in it. Anything without an I is a constant in the sum. So I pull that out. And then what can I do across this plus sign here? Sums break up, right? You can distribute the sum across the plus sign. So this is really 1 over 1,000 times the sum I equals 1 to 1,000 of 1 plus 1 over 1,000 times the sum I equals 1 to 1,000 I over 1,000. You guys see what I did? This guy went here and here. But because the 1 over 1,000 was out front, it goes to both of them. Now what? This pulls out again. 1 over 1,000 is a constant multiple for this guy. It wasn't here, but it is here. So let me rewrite this one. this guy is another constant. This guy is a constant multiple of 1. This is like I times 1 over 1,000. So this one. So you'll have 1 to 1,000 of I, but then you'll have 1 over 10,000? Or, no. Million. Zeros. 1, 2, 3, 4, 5, 6 zeros. Which is beautiful, even though you don't believe me, because each of these I know. If you sum up 1 from 1 to 1,000, what do you get? 1,000. Right, that's this guy. 1 from 1 to n is just n. So 1 from 1 to 1,000 is 1,000. But keep the constant multiple. Plus constant multiple times what this guy sum up to. 1,000 times 1,000 plus 1 over 2. You can add them up now, cancel a little bit. 1.50. This will be 1,001 over 2,000. So 2 point, what is it? 0.00005? Like that? Is that too many zeros? Oh, no, this is almost a half. Sorry, I was thinking of 0 and a half.
0.50.
0.5.
0.005.
0.005 like that. This is just about a little bit over a half, so that makes sense. Alright, so now you're exposed to sigma notation and you see how tedious and confusing and dull it is. But it's useful. It's a tool and it's useful. I'm using calculus now. We'll actually apply this to the area under the curve. Okay, so now we're talking about, that was kind of the preliminary stuff. At some point in your life, maybe you should have seen that, but most of you haven't, so we went over. Now we go back to calculus. Area under the curve. Let y equal x squared plus 1. All right, so I'm giving you a curve. Suppose, so let y equal x squared plus 1, but I'll give you a domain. So 0 is less than or equal to x is less than or equal to 2. I want to estimate the area between the curve and the x-axis using 4 rectangles of equal width. Now, the point of this example is to show you sort of how the ambiguity of the statement, because just saying 4 rectangles doesn't really give you enough information to specify exactly one area. So let me show you what I mean. I can choose, by the way, what is the graph of x squared plus 1 look like? Parabola pointing upward or downward? Upward, what's the plus 1 do? Shifts it up. So here's my curve. Something like that. I want to estimate the area, but I'm only on the domain 0 to 2. That would be a 4. I want to estimate this area here, 0 to 2, the area between the curve and the x-axis. So I'm trying to get an estimate of this area. It tells me to do it by drawing 4 rectangles of equal width. So the idea is, in order for my rectangles to be equal width on the interval 0 to 2, how wide do they have to be? Yeah, so you have a total distance of 2 minus 0 to cover, right? You can always do your right endpoint minus your left endpoint to get the total distance you have to cover, and then divide by the number of rectangles you want. So this will always give you the size of your rectangles. You do the length of the interval over the number of rectangles. If you do this, 2 over 4 is 1/2. So if I want rectangles of equal width, I have to make rectangles of width 1/2. But I can still draw a bunch of different possibilities. There's 3 common possibilities you'll see. So you'll see what's called upper sums, lower sums, and midpoint. So there's 1, 2, 3 halves, 1/2. So the way upper sums work is you draw rectangles that are above your curve. So for example, at 1/2, you draw this rectangle. So you go up to the function at 1/2 and draw a rectangle that's actually above the function. And if you go to 1, and go up to the curve, you draw another rectangle of width 1/2. 3 halves, you go up. Oops. Go up to the curve. You draw another rectangle of width 1/2. And 2, you go up. You draw another rectangle of width 1/2. These are called upper sums. Because you're overestimating the area. It's above the curve. Or you can do lower sums. What do you think lower sums will do? Stay below the curve. Here's 1/2, here's 3 halves, 1, 2. So lower sums start, in this case, they start from the left so that you can draw a rectangle that has width 1/2 that stays below the curve. So you go up to your curve on the left, and you draw a rectangle. These are the questions. And using the midpoint, here. That one's even more annoying. Here's my curve. But in order to have a midpoint, to use rectangles that hit at the midpoint, you have to subdivide into your four 1/2 width rectangles. But where do you think, for the first rectangle, I can't use the left part of it to go up, and I can't use the right part of it to go up. If I'm doing midpoints, I have to use the middle of this subdivision, and go up to the curve. So the midpoint rule, when you use the midpoint rule, you'll have a little bit above the curve and a little bit below the curve. So if you take the midpoint here and go up to your curve, a little bit above, take the midpoint here, above, midpoint, above, so each one of these is an estimate of the area under the curve using 4 rectangles of equal width. And since I didn't really specify, do any of it. Okay? In general, though, I will tell you what I want you to do. I either want upper sums or lower sums or midpoint sums. But I needed to draw you each one so you saw the difference. So let's see if we can get the area in each case here. So in the purple case, when I'm using upper sums to estimate my area under the curve, what am I going to do? Remember, in each of these cases, the curve is given by y equals x squared plus 1. I know, in the purple case, say for example, for this first rectangle, what's the width? 1/2. What's the height? What is it?
1. Or
So in the purple sums, the height of the rectangle comes from taking 1/2 and going up to the curve. So for the first rectangle, you would do 1/2 for the width times 1/2 squared plus 1 for the height. Where did I get this from? Plugged into the formula. Right, so the width comes from this calculation right here. This is the width of our rectangles. But then the height, or the length of the rectangle, comes from plugging the correct endpoint into the curve. So what would I add up after this?
another 1/2.
1/2, because the width is 1/2 for the second rectangle, times 1 squared plus 1. Right, because for the second rectangle, I go to 1 and go up to the curve. So I plug 1 into the curve. Plus 1/2 times third rectangle, 3/2 squared plus 1 plus 1/2 times 2 I wouldn't waste a whole bunch of time. I would put this in a calculator. And if you're supposed to find the area, estimate the area, I would put this in a calculator, right? This will be 0.25 plus 1 and then multiply by 0.5 and just add it all up. You should try it and see if you get 5.75. So that's with upper sums. By the way, if I wanted to write this in sigma notation, like if I wanted to take this sum, this plus this plus this plus this, and write it in sigma notation, what would it be? I equals
N equals 4.
1 to 4, right? Because you have 4 terms. And then just look for the pattern. Each one of them has 1/2. Now, should I do I squared plus 1? Is that correct? Is that what's happening here?
No.
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 So when I is 1, you actually have I over 2. And then you square that. This is 1 over 2 squared. This is 2 over 2 squared. This is 3 over 2 squared. 4 over 2 squared. So you actually have 1/2 I over 2 squared. I was just kind of reviewing them. What? Go ahead, question.
Can you pick what method you want to do?
Yeah, unless it says.
Unless you
Yeah, I will usually specify. I'll say use lower sums or use upper sums. If I'm being really mean, I'll say use midpoint. What about for lower sums? What do we get? So lower sums are the green. What changes here? Not the width of the rectangle, right? The width of the rectangle is still the same, 1/2. Right, so when I start adding up the area here, I'll start with 1/2 times what? So what changes, instead of going on the first rectangle, the right endpoint doesn't go up to the graph. The 1/2 doesn't go up to the graph on the first rectangle. The 0 goes up to the graph. So the left side is always going up to the graph. So in this case, I would do 0 squared plus 1. Plus 1/2 times 1/2 squared plus 1. Because on the second rectangle, if you go to the 1/2, that's what goes up to the graph. Plus 1/2 times 1 squared plus 1. Because on the third rectangle, the 1 goes up to the graph. 3/2 squared. I got 3.7. Does that make sense? It's always the same. It's always the same format. You're going to have the width of your rectangle times the height of your rectangle. But the height of your rectangle, you just have to make sure you plug in the right value. Right? You either plug in the left. So here on this one, you plug in the left side of the interval, the left side of the rectangle, or you plug in the right side of the rectangle. going to happen here? Yeah, so now we have to figure out exactly where the halfway point is on each of these intervals. Between 0 and 1/2, 1/4 is halfway. Right, between 1/2 and 1, 3/4. Between 1 and 3/2, 5/4. And between 3/2 and 2, 7/4. So in order to get the area here, what would I add up? What's the width of each rectangle? 1/2 still. And then for the first rectangle, how high do I go? 1/4 squared plus 1. Because I just plug in the quarter. For the second rectangle, what do I plug in for the height? 3/4. And I plug in 5/4. I plug in 7. Which one's going to be the best estimate? Midpoint, because you have a little bit of over area and a little bit of under area canceling each other out. Right? This is a little bit over, this is a little bit under. Here, it's all under. Here, it's all over. That's how you approximate the area under a curve. Questions? As long as you draw a picture, as long as you have a decent picture, I think it's pretty easy. But to tell the difference between upper and lower sums, it's best to have a picture. So example. Estimate the area under the curve. Y equals 3 over x from x equals 0, x equals 50. Using let's do upper sums. 2 equal length rectangles for equal width rectangles. And we'll do lower sums. Let's practice with that. 4. So let's see if we can streamline this process here. Estimating area under the curve, upper sums, 2 equal length rectangles, y equals 3 over x from 0 to 50. Let's see. What does 3 over x look like? what's 1 over x look like? Yeah, it's got an asymptote at 0. It's a reciprocal function. So 3 over x is just 3 times 1 over x. So it's a stretch. So I'm estimating the area from 0 to 50. I want to use, for part A, 2 equal width rectangles. So if I'm going between 0 and 50, and I want 2 equal width rectangles, what am I going to have for my width? 25. Right, 50 minus 0 over 2 tells you your width. The length of your interval over the number of rectangles. I can't do upper sums. Let's do midpoint. I changed it from my notes and it screwed me. You see why it screwed me? Why can't I do upper sums on this? Because it's an asymptote at the stupid left-hand endpoint. So stupid. If I try to do upper sums, I have to go all the way up here and do a rectangle. You can't do it because it's an asymptote.
It'd be overestimate.
It'd be a drastic overestimate. That's assuming this area is finite. We don't know. But let's do midpoint first, and then we'll do lower. So how would I do midpoint here? I have to find the midpoint of my first rectangle, which will be 12.5. And then I have to go up and draw a rectangle. Now I find the midpoint of my second rectangle between 25 and 50, 37.5. Draw another rectangle. So the area here is approximately what? What's the width of my rectangle? 25. What's the height of my rectangle? You have to plug in 12.5 to function, right? So 3 over 12.5. That's my first rectangle. Plus 25 is the width times 3 over 37.5. And you put it in the calculator. I got 8.
I was confused about the number 3, but it's from.
Yeah, 3 is from the, it's in the formula. So that's part A. Not too bad, right? Why was this not too bad? Like 2 rectangles, right? If I give you 2 rectangles, it's pretty straightforward. I give you 20 rectangles. I'm just trying to get you. So for B, I want 4 rectangles and lower sums. So the function doesn't change. The domain doesn't change. I'm still going from 0 to 50. The way I draw my rectangles is going to change. Lower sums means you stay under the curve. So I need to recalculate my width as well, since I have 4 rectangles. What's my width going to be now? 12.5, right? You do 50 minus 0, because that's the entire width, the entire length of your interval, divided by 4 rectangles. So 50 over 4 is 12.5. This is the width of each rectangle. 12.5, 25, 37.5. And then to draw lower sums, I have to stay underneath the curve. So at 12.5, 12.5 I go up, stay underneath the curve. 25 I go up, stay underneath. So this is the area. So what do you think? What am I going to do here? What's my width for each rectangle? 12.5. And for the first rectangle, what's my height? How high is this first rectangle?
And we're
Plug it in. 3 over 12.5, right? You have to get the height, you always have to plug into the function. Plus 12.5 times, what's the height of the next rectangle? 3 over 25. Plus 12.5 times 3 over 37. Plus 12.5 times 3 over 50. I didn't actually do this one out. 5.5, 6.25, 0.25. I don't know, did somebody do it? Calculator, check me. Is that what you got? Okay, easy enough? Okay. I'm gonna get a lot less than I want to stop estimating. I want to start finding the exact area. Find the exact area under the curve y equals x squared from x equals 1 to x equals 2. So kind of the idea here. Not to scale. So the idea here is I have a curve, x squared. It's got 0, 0, 1, 1, 2, 4, 3, 9. And this other part, but I'm not really care about this. X squared. I can estimate the area under the curve by drawing a bunch of rectangles, right? The more rectangles I draw, the better my estimate is going to be. Right? Here's 6 rectangles, crappy rectangles. But just so you see what I'm. All right, that's a decent estimate. It's okay, it's not great. I could do even better if I doubled this. erased all this, and I said instead of 6 rectangles, I want 12 rectangles. So one here, one here, one here, one here, one here. All right, I keep going. Each time you increase the number of rectangles, you get slightly less extra area. So if I want to find the exact area under the curve, then basically I need an infinite number of rectangles. So I'm going to set up a limit process so that I can take a limit as the number of rectangles goes to infinity in order to get the exact area. I'm going to design everything the same way, but I'm just going to do it with n rectangles instead of 4 rectangles. And then I'll take n to infinity. So for example, I want to find the area under this curve with n rectangles. Well, what's the width of each one of my rectangles going to be? Oh, I want to go from 1. 1 to 3. So from 1 to 3, if I want to use n rectangles, what's the width of one of my rectangles going to be? So with n rectangles, I have to cover this distance here from x equals 1 to x equals 3, because that's what it says here. I have to cover this distance, but I do it in n subdivisions. So the width of each rectangle is going to be 2 over n. Right? If I had 4 rectangles, it would be 2 over 4. If I had 10 rectangles, it would be 2 over 10. But I want to keep it in n so I can let n go to infinity. So here's the tricky part. Here's my parabola. Here's x equals 1. If I want a rectangle, and it's not going to matter whether you do lower or upper sums. I drew upper, so let's keep with upper. If I want my width to be 2 over n, where is my next point going to end up? Like if this were 2 over 4, it'd be 1/2, right? So my next endpoint would end up at 1.5. If this were 2 over 10, then it would be 0.2. So my next endpoint would end up at 1.2. But if I keep it 2 over n, then my next endpoint is going to end up at 1 plus 2 over n. You just add it. You add the width of your rectangle to your starting point. And then I have to have another equal length rectangle. So where's my next endpoint going to end up? 1 plus 2 over n plus 2 over n. Does that make sense? You just keep adding 2 over n. So it'll now be 1 plus 4 over n. Go out to your next one. But you add another 2 over n. What do you think you should be at? 1 plus 6 over n, right? Because you add another 2 over n. And then we're going to keep going until we get to 3. So let me, I'll start this and finish it up. But let me get an expression for the area written, and then I'll show you how to evaluate it next time. So if I want to get the area by doing upper sums like this, and keep going until I get to 3, what am I going to write here? Area equals, what's the width of my rectangle? 2 over n times what's the height of the first rectangle? 1 plus 2 over n squared, right? Because you have to plug it into the function. The function is y equals x squared. So you take this guy and plug it in. 1 plus 2 over n plus 2 over n times 1 plus 4 over n squared, because that's my next endpoint. And you keep going until eventually you're going to get to 2 over n times 3 squared, right? Because your last rectangle will end at 3. So the area under the curve, the exact area under the curve, will be what we get if we take the limit as n goes to infinity of this expression. And that's what we'll do next.
Why is that last term 1/2? Was it a mistake?
Oh, that was 2 over n. Where did I get 1/2? So then we can do 1/2 of 5. Turns out that to actually evaluate this, you really want to put it in the sigma notation. To evaluate this limit, you really want this in sigma notation. But anyway, that's what we'll do next time, because I'm out of time. All right, and that's kind of where 4.3 starts. All right, so 4.2 is a lot of the estimation, and 4.3 is actually evaluating this limit.